Hello everyone, our project is real-time collision-free navigation of multiple autonomous vehicles. So let's dive right into it. So let's first understand what are the problems we are trying to solve. Imagine we have a map wherein the vehicle has a start and goal defined, and now there are some static obstacles in the map, some non-reactive dynamic obstacles, and then there are some vehicles that are similar to ours, so they basically react to the opposite vehicle as well. Our goal is to enable them to reach the goal node, and maybe there might be multiple autonomous vehicles who have a start and goal node. And the main thing here is that we do not have any communication between these vehicles. So this is a totally decentralized system. So how would we approach this problem? So the problems that we have tackled in this project are first is that the vehicle is non-holonomic. Hence, we need to adopt a bicycle model. Then second is how to effectively avoid these dynamic obstacles. So we have applied the following algorithms, that is velocity obstacle, optimal reciprocal collision avoidance, acceleration velocity obstacle. And also finally we need a planner. And here we have assumed that we have a global planner, that is the A star, which provides us the set of goal nodes. And then finally we have a local planner that plans the path between these nodes. So to build a strong understanding and background for the project, we focused on mainly four domains. First is the general review, then the kinematic models, the velocity obstacle, and the different control techniques we can use. The first problem is the formulation of a bicycle model. So here we have assumed that we have the states that are the position XY, orientation angle, and the steering angle. Also, we have decided to take the control inputs as a velocity and the steering rate. By steering rate, we ensure that the steering angle would be more smooth. So this is the final state space model equation as shown. Next, let's understand the velocity obstacle avoidance. For the purpose of the project, we have explored the following methods. The generalized velocity obstacle, reciprocal velocity obstacle, optimal reciprocal collision avoidance, and acceleration velocity obstacle. So basically, this is helping us avoid the multiple obstacles that are moving dynamically in our environment. So let's understand each of these methods and their limitations. So first is the generalized velocity obstacle. So assume we have a vehicle A and we have the vehicle B, and both are formulated as a disk. So we can easily inflate this B to a bigger disk using the Minkowski sum, and we can then form the velocity obstacle cone and translate it by some distance, that is the velocity of the B obstacle. So here, using this, we can easily formulate a minimum time equation, which gives us the time under which the distance between these two would be minimum. So it is a direct analytical solution for holonomic robots. But here we are using a non-holonomic robot, and hence there's no simple analytical solution for this. Hence, what we can do is we can formulate this as a cost, and we can do it for multiple positions of the A robot. So we propagate the B obstacle for some distance, and same thing we do for the A for tau sampling time. And then we use the inverse of the distance between them to take it as a cost into our MPC. This detailed explanation of cost would be explained later in the MPC part. The limitation here is that it is not efficient when there are similar vehicles in the environment, because there happens to be act known as the reciprocal dance which occurs, which will be explained in the next slide. Also, the acceleration is not considered of the obstacle. So if the obstacle is accelerating at using some acceleration, then the robot might not be able to judge it perfectly. So now I had mentioned something as the reciprocal dance. So what is that? So what happens is when another vehicle that has a similar reaction to us comes in front of us, we observe that in this diagram that they both deviate from the path. Then they observe that the obstacle is no longer in its course. So it again becomes straight. But then again realizes that, oh no, we are going to crash. So they keep doing this dance. And to tackle this, there is a method called the reciprocal velocity obstacle. Here the method is simple. All the formulation is done similar to VO. And now once we give this cost to the MPC, it returns us back a velocity. And what we do is take the average of the current velocity of the robot plus the optimized velocity which we got and take its average. And this is given as the next control input. And here the limitation is again that we have not considered the acceleration of the robot. Hence we come to our final method, that is the acceleration velocity obstacle. Acceleration velocity obstacle. This method assumes that acceleration is measurable for the obstacle. We can do this by taking the velocity difference between both and dividing it by the sampling time. Next, we formulate an acceleration velocity obstacle. Basically, we take the robot and propagate it for tau sampling time, similar to a velocity obstacle method. And similar process is done for our vehicle as well. Now, at this each position, we calculate the cost using the inverse of distance. And finally, the control input that is fed to the robot is as shown below. So now we have understood how we are going to avoid the various obstacles. So let's move on to our proposed planner. First is to design a local and a global planner. So here we can see that we have the start to goal defined, and the global planner makes these blue dotted line path. And if everything goes well, the local planner does not need to do much of its job. But there's possible that it has a lot of obstacles in the way, and it has to make a different path. So let's now first understand the global planner. We can approach the global path planning problem in two ways. First is we randomly sample n nodes in the map, and this is how it would be. And connecting these nodes to its k nearest neighbor using the builded weighted graph. Second, since this is an application domain of an autonomous navigation, a better approach would be to sample nodes only at the junctions or on the map. This is computationally cheap, but it is, however, assumes that the knowledge of the map already exists, which is usually the case when we have GPS data. So now once we have so many nodes, we can decide a start and a goal, and finally use A star to found the path. So for the purpose of project, we have assumed that A star returns us these goal nodes along with the orientation desired at each goal node. Now let's move on to the local planner.
Now, the global planner has provided the desired goal states. We need a local planner to ensure we reach our goal nodes. Here we opted for a model predictive control. The major parts of an MPC are state model, that was a bicycle model that was defined earlier, objective function, and an optimizer. Here we use RMS prop as our optimizer. Some of the important terms to understand model predictive control are sampling time, that is the minimum time step or the measurable time step or the discrete division of the time that we will be using. Prediction horizon is the number of future sampling time intervals that the controller must evaluate for the prediction and then optimize the objective function on that. Model predictive control is an optimal control strategy which consists of state model objective function as an optimizer as mentioned. Here with x0 as the initial state of the system, at each sampling time tau, the state model is used to predict behavior of the system over n tau planning horizons. The optimizer optimizes the future control input and minimizes the objective function over the entire planning horizon, therefore providing a sequence of optimal control input. However, only the first control input is applied to the system. The same procedure is repeated with updated x0 and shifting the sequence of control inputs further. So this is your diagrammatical representation of what I just said. Now let us look MPC in a little more detail. Here, this slide presents the state model of the system where x of t represents the state of the robot or the vehicle at any time instance t. U of t represents the control input, that is the velocity and the steering rate. And the motion model here represents that any state of the vehicle can be calculated by the initial state plus integrating over the all previous states. This is the kinematic model that was shown earlier. The objective function of the MPC problem is a optimization problem that is optimized using an optimizer. Here, for our case, the objective function consists of the following cost, that is the goal reach cost, that is the quadratic distance between the start and the goal, smoothness cost, that is how the control input evolves over time, constraint cost, that is the maximum and minimum bounds of the control inputs, deceleration cost, that the robot should be at halt at the end, then collision avoidance cost that involves static and dynamic collision avoidance. This is in detail the objective function formulation. The goal cost represents the distance between the start and the goal. Here the constraints are reformulated again as a cost so that it can be added to the objective function. This term represents the smoothness cost. Here this term is the deceleration cost of the vehicle, and this is the obstacle model, that is how the obstacle is added to the objective function and how it is avoided while optimization. According for dynamic obstacles, we assume that the sensor obtains the data of position, orientation, angle, velocity, acceleration. Based on the method, we decide which information is important. Next, using a linear model, we calculate the future position based on tau sampling time, which can be equal to the prediction horizon or more than it. Now, using the cost shown this here, we add this to the total cost, and this is how we involve VO, RVO, and AVO methods in our objective function. The next step is to find the total cost by weighting the cost formulated earlier. The weights are the tuning parameters for the vehicle. This cost formulated is now optimized using an optimizer such as RMS prop or ADAM. For the purpose of our project, we opted for the RMS prop optimizer. Here we calculate the gradient of the cost using the autograde function in the Python. The learning rate is a tunable parameter. Here the constraint is added to the denominator to avoid the infinite gradients.
So the implementation of this is done using the toy problem in Python. Here, to simplify the computations for configuration space, the autonomous vehicles are assumed to be a circle of radius R. However, these vehicles still follow the kinematic bicycle constraints. So here we are inspired from the Lamborghini, Ferrari vehicles, and basically the dimensions are made using the Lamborghini Aventador. Next, the static obstacles are considered to be circles, and the dynamic obstacles are the police car and the taxi car. Now, the performance metrics are as follows. We find how much is the time to complete the task, what is the clearance to the obstacles, the smoothness of the traverse path, that is, we also check the smoothness of the velocity inputs, the steering angle, the orientation angle, and finally, we calculate the overall length of the traverse path, both the global path planning and the local path planning. So now let's move on to the experiments. So let's start with the first experiment, which is the operation of MPC under static obstacles. So here we can observe that we have two static obstacles and we have a set of goal nodes that is provided by the A star. The vehicle successfully avoids these obstacles and finally reaches the goal position and also decelerates using the deceleration cost. Here we can observe that we have a distance to goal where we can see that the vehicle has reached zero position and also the orientation and steering angles have a desired of 0 degrees and that has been successfully achieved. And also the obstacle distance is also above this red line, hence there is no collision. And here are the velocity and steering graphs as well, which are well under the constraints. So here, let's now incorporate some dynamic obstacles. So here we have a police car that's moving towards the vehicle. So remember here the MPC is doing the avoidance using static obstacles basically. So it's assuming this as a static obstacle for different iterations of time. And hence it works well when the obstacle is coming right at it. But what happens if we provide obstacles from the side or in an angle? So before we move on to that, let's look at the graphs. So here we observe similar properties that we reach the goal and the orientation angle and steering angles are nearly zero at the end, which is the desired angles. And here the obstacle has been avoided. Also here are the velocity and steering rate, which are the control inputs for our car. So now let's see what happens if we provide an obstacle at an angle towards it. Can the MPC with dynamic obstacle avoidance avoid this obstacle? So here we have two dynamic obstacles. One is the taxi and other is the police car. And here we see that it's trying its best to avoid it, but since it does not know its velocity, it cannot exactly formulate its direction and it crashes with both of them. And this is a hypothetical scenario where it would reach the goal. But yes, now let's see the graphs. Here we can see that in the distance to obstacle graph, it has collided with both the obstacles, and also the steering reach have almost reached their constraint limits. And this is because the cost to avoid these obstacles had gone so high that it still did not care of what its steering rate should be. So now let's see if we can incorporate the velocity obstacle to avoid such a scenario. So now using the velocity obstacle, we take the similar conditions. Even the velocities for the robot, the vehicle are similar. And here we see that it effectively avoids the taxi and the police car, and it plans its path well according to the velocity of those obstacles. So now let's look at the graphs. So here we can see that it effectively avoids the obstacles, and the steering rates are within the limits in the upper bound, but the lower bound it has almost reached. This is because it had to avoid those obstacles, but still it has successfully maintained that bound, and so it works well. So now, can VO perform satisfactory if we have different vehicles into the picture? Let's see. So now here we can see that we have multiple vehicles that are going to behave in a similar way that we are. So let's see how velocity obstacle performs in such a scenario. So they decide their paths effectively, and it's quite pretty correct. And it looks like velocity obstacle performed really well. But let's dive deep into the graphs so that we can understand what are some of the loopholes of this problem. So here we can observe that the steering rates have been plotted for all the three cars, and we can see that there are some kind of staggered response, and these are the oscillations that the authors had talked about in the reciprocal collision avoidance paper. This is nothing but the reciprocal dance, where the vehicles dance around each other because they think that they have avoided the obstacle, avoided each other, but in fact they haven't. So they again change their paths. So to tackle this issue, we introduce the RVO formulation into the problem, and we'll see the results for it as well now. So now the same simulation is performed for RVO, and judging by how it looks, it feels that they are performing the similar way as velocity obstacle was. But trust me, there's some better thing that's happening here, and we can see that in the graphs. So let's move on to the graph. So above there are three graphs for yellow, red, and blue vehicles, and we can see the steering rates are way smoother. And here is like a comparison, and this was effectively done because it took an average of its current input and the optimized velocity which it got. And we can see that it takes a longer path of 97 meters while this is 96.97, but at the same time the time taken is less, so it's effectively avoiding those oscillations and giving a faster reach time even though the lengths are slightly higher. So we have observed that VO and AVO are both powerful, but what happens if we bring an accelerating vehicle into the picture? Here the police car is accelerating at 8 meter per second square, and we can see that the VO starts losing its calculations and it eventually collides with the police car. So let's look at the graph to show that it actually collided. So we can observe here that the vehicle has actually collided with the obstacle, and in order to even avoid this, it threw its steering rates all over the graph, and it's way above the constraints. And this has happened again because it considered the cost of collision so high that it started ignoring the steering rate constraints. And this is a problem for VO when it sees an accelerating velocity obstacle. So now let's introduce the concept of acceleration velocity obstacle, wherein we consider the acceleration of the other vehicle and also use a constant acceleration for our model to propagate in its prediction horizon or the tau sampling time. So here we have a similar situation where the police car is accelerating at 8 meter per second square, but here we see that the vehicle effectively increases its velocity and it avoids this obstacle. So this it's slightly confusing to understand what actually happened. So let's overlay both these results. But before that, let's look into the results of the graphs.avo. So here we can observe that the distance to obstacle graph, and we can see that it effectively avoided the obstacle. And also the steering rates are now within the constraints and pretty smooth as well. So now, as I said, let's overlay these both outputs into one single simulation and see what happens. So here I'm going to simulate two vehicles. One is with AVO and one is with VO. And remember that they do not know each other. So I have done this so that I can show you how both are reacting to this single dynamic obstacle. So let's see what happens. So here we see that the yellow vehicle, which is under AVO, starts accelerating to avoid this obstacle, while the red car is not able to do the same as it has the VO formulation. And that's why AVO is slightly better than VO when it comes to accelerating vehicles. So now let's put all these pieces together and observe the performance of MPC with the velocity obstacle methods. So before I start the simulation, I would inform that the yellow vehicle and the blue vehicle, they are having the AVO formulation, and the red and the green have the VO slash ORCA formulation. So let's see how the simulation runs now. So first, we'll see how this yellow vehicle is able to avoid this police vehicle, and it effectively avoids it by going it from the other downward side because it knew its acceleration. And here the blue and the red vehicle avoid each other successfully, so proving that it is able to navigate with similar vehicles in the environment. And the green vehicle is going slowly as it knows that it has tighter turns, hence it's able to reach its goal. And here we can see a difference in the AVO and VO, that the blue and the yellow vehicles have an oscillating nature. So let's look into it in the next slide. So here we can see the drawback. So this is the one in which all of them are at AVO. So I have simulated a condition where all are using AVO, and we can see all of them are oscillating a lot. And this kind of resembling a PID controller graph, and this is happening mostly because the accelerations are not varied in a correct way, and this is kind of a limitation of the acceleration velocity obstacle. Also now, looking at them at side by side, we see, so we can mainly focus on the green and the red one. So the red and the green one here is with the VO formulation. It's pretty smooth and less oscillations, while acceleration velocity obstacle has some oscillations. But we cannot always use VO. Like for the yellow vehicle, it was trying to avoid this accelerating velocity obstacle, and VO would fail in such a scenario. So we need to find how we can better improve this acceleration velocity obstacle to mitigate these oscillations. So we have seen a lot of experiments, and based on that, we have some conclusions to make, and we can decide on what our future work could be. So first is like, for car-like vehicles, a non-linear MPC is employed, for which a closed-loop solution for the optimization of the objective version does not exist. Hence, we use an open-loop optimization problem that is solved at every time step, and this makes it very computationally expensive. And also the project only implements a try problem. So assume that the MPC optimization is completed within one time step, and a new control input is fed to the vehicle after every time step. So in a real world scenario, this might not always be the case due to the limitation of computational. Third is that no alternative approach for mitigating the most advanced AVO method is provided. Uh, Also, the fourth one is that we have assumed that A star provides us the desired orientation of the vehicle at intermediate nodes. So not only the position, now we also know the orientation using A star, which is quite tricky because you do not know where the vehicle is moving. So this can be like used with the mathematical formulation can be done by calculating the desired orientation at those intermediate nodes based on the vehicle's current position. And this can help in solving this issue and then making this project more robust. The contribution breakdown of my work and Fennel's work as well. So thank you, and I hope you like the project. great day. Thank you.